Okay, so for vertical asymptotes, we know that the line x equals a is a vertical asymptote of the graph of the function y equals f of x if either the limit as x approaches a from the right is equal to positive infinity or negative infinity, and the limit as x approaches a from the left is positive or negative infinity. We find vertical asymptotes by setting the denominator of any function equal to 0 once we've totally simplified. So you can't immediately set the denominator equal to 0. It has to be after you've simplified, because we have what we can call removable discontinuity, and that can eliminate a vertical asymptote. So a vertical asymptote occurs after you've simplified all the algebra. To find out if a function has a vertical asymptote, we need to determine where the function is undefined. So we know in mathematics we can't divide by 0, so the function will be undefined where it's division by 0. To do that, you set that denominator equal to 0 and solve for x. Where graphs have vertical asymptotes, the function will have what we call an infinite limit. So where they have a vertical asymptote, we have what we will call an infinite limit. This means that the limit of f of x as x approaches a is an infinity, or more simply,
Now you have proof.
or more simply, yeah, that's just terrible. Or more simply, that f of x is increasing or decreasing without bound as x approaches a. So if you didn't catch me saying all that, you may want to read it one more time. So, the question becomes, what are the vertical asymptotes of the function f of x equals 2x over x minus 3? Describe the behavior to the left and to the right of each vertical asymptote, and find what those infinite limits are. So, let's do that. Can we simplify anything from the numerator to the denominator? No. So what we're going to do is then set the denominator equal to 0. So we get that we have a vertical asymptote at x equals 3. Knowing that I have a vertical asymptote at x equals 3, I now need to figure out what is the behavior to the right and what is the behavior to the left at x equals 3. So what I'm going to do is I'm going to look at each of those limits by plugging in values to the left and to the right of them. So if I look at the limit as x approaches 3 from the left of 2x quantity x minus 3, what I want to do is plug in something to the left of 3, so 2.9. So what we're going to do is look at 2 times 2.9 all over 2.9 minus 3. And again, all I care about is the sign, because I know it's an infinity. It's just whether is it positive or negative. So a positive times a positive is a positive. 2.9 minus 3, however, is a negative. Therefore, the limit as x approaches 3 from the left of this quantity is negative infinity. And you'll notice I'm not using equal signs. I'm not using equal signs because I didn't plug in an infinity here. I plugged in a number. So this is not necessarily equal to that. So in mathematics, if you're not doing something totally mathematically legal, do not put equals. Put arrows. Arrows are saying, all right, this is kind of what I'm doing, but it might not be mathematically legal, so to speak. Because if you put an equal sign, AP will say, no, thank you. Like, that is not equal. That is not the truth. If I took away this middle part, right, so like if I didn't show that, then from here to here, I could put the equals. Because the limit is negative, does equal negative infinity. But I can't show the middle work. Does that make sense? So the limit as x approaches 3 from the right is going to be a positive infinity, because think about it, if you plug in something like 3.01, positive times a positive is positive, 3.01 minus 3 is now 0.01, so we get a positive, so positive divided by a positive gives positive infinity. So the behavior to the left and to the right is as such. That means that if I wanted to sketch what is happening, I know that to the left of 3, we're going down to negative infinity, and to the right, we're going to be at positive infinity. I don't know what's happening in between. These could be overlapping. They could be doing anything. I do know, though, think about it again, if I asked you, what is the horizontal asymptote? If you have an x on top and an x on bottom, yeah. Because the coefficients, remember? So this has an x of 1, this has an x of 1. So since the degree of the x's are the same, it's their coefficients. Okay. Yep. That's why we keep going back and we keep talking about what we already discussed. Because we're still putting all the pieces together. So that means at 2, we have an asymptote. So without putting this into a graphing calculator, I would predict my graph looks something like that. It may not be perfect. It may not be right. This could go through 2 on this side, but maybe not on that side. But if I was predicting quickly, that's what I would predict. Okay, so it says find the vertical asymptotes of f of x equals tan x. So we know that the tangent of x has many, many, many vertical asymptotes, because the tangent of x has many, many points of discontinuity. Those points of discontinuity occur at all of the key points in which the cosine is 0. So you have to say to yourself, okay, if I'm talking about f of x equaling tan x, I'm talking about sine of x over cosine of x. So remember that the vertical asymptotes come from when the denominator of a function is 0. So you have to think about the fact that tangent is really sine over cosine. So to find the vertical asymptotes of tangent, we have to say that the vertical asymptotes occur at cosine x equaling 0. So when is the cosine of x equal to 0? Well, it's equal to 0 at pi halves, 3 pi halves, and all cycles of that. So what we can do is say that it is equal to pi halves plus k pi, where k is any integer being added or subtracted. So happy my pen writes. Are we okay so far? So we have defined the vertical asymptotes in terms of A. So I know I wrote X, because X is how we write a vertical asymptote. So what that means is when I'm looking at these limits, we're looking at the limit as X approaches pi halves. We're going to talk about it from the left. And the limit as X approaches pi halves. And we're going to talk about it from the right, because that behavior is going to repeat itself. So if you think about this, we have all students take calc. So we know that the asymptotes occur here and there. So if you think about it from the left in terms of graphing this, we're talking about coming from quadrant 1. So if we're talking about the limit from quadrant 1, all trig functions in quadrant 1 are what? Positive. So if we're talking about the limit from the left, what do we predict the tangent infinity to be? Positive. So go ahead, take your calculator, and let's do it side by side so you can see exactly what I'm saying. So in your y equals, I'll do it with you. Go ahead and plug in tan x. And then what we're going to do is we want to look at our limit. So we're going to put pi halves in the middle. So go ahead and y1, put tangent of x. Make sure two things. Make sure your mode is in radians and not degrees. And then for your window, since we want pi halves to kind of be in the middle, let's make the x max 0, and we'll make the x min 0 and make the x max pi. And then make your scale pi halves so that we're sitting right with pi halves in the middle. Tangent we know is infinite, so the negative 10 to 10 window scale is fine. And then again, you can see exactly what I'm saying. As you approach from the left, because we're technically coming from quadrant 1, the limit will go to positive infinity. Does that make sense though? Like, can you see that? So then think about the fact as you're coming from the right. From the right, all of the sine values are positive, but the cosine values are negative. So you're going to have a positive divided by a negative. Therefore, this is going to be a negative. All right, let's try again. Let's make sure we've got this down. We know that there's another horizontal asymptote where on tangent? Yeah, down here, right? At 3 pi over 2. So 3 pi over 2 coming from the left. So again, if you want to change your window, you totally can, because now you can make it pi to 2 pi. But again, 3 pi halves coming in from the left means we're coming in from here. Down here, both of these are negative. So negative divided by negative is a positive. So you see how like this is the same as that? And it would be the same again if I went up here and I added, pi again. They're always going to be positive, negative. So limit as x approaches 3 pi halves from the right is negative. Okay, if you look at the graph, did the graph even look different when you changed your window? No. If you want to see the true graph, you could make your window 0 to that 2 pi, and then you'd see 2 cycles of tan. And then you kind of see the tangent you're used to seeing, right? When you guys learn tangent, you actually You kind of didn't learn it 0 to 2 pi. You kind of learned it negative pi halves to pi halves. But this is like the true look of it. Yeah, Anna?
I'm confused on why the first line is positive.
This one?
Yeah, because aren't you going at it at the left side?
So think about the way the unit circle works then. So when the unit circle starts, this is quadrant 1. And then I'm going to do it in yellow so you can see me. So you start in quadrant 1 right here. So this is at the sign of 0, let's say. Then we go this direction, because that's sign of pi halves. Then you go to sign of pi. So as you go counterclockwise on the unit circle, you get bigger. So from the left, so the left is coming from the small side, you're coming from quadrant 1 to quadrant 2. Let me think if I can. Sine function. This right here represents the peak of, or not the peak, it represents pi. It represents the end of quadrants 1 and 2. So when we have it seen as a graph like this, we can totally see coming from the left. Technically, this point right here is pi halves. So tangent is sine and cosine put together. Then technically when you're coming from the left, you're looking at both of these at pi halves as individuals. So if you come from the left here, is this positive or negative on sine? Remember, positives are above, negatives are below.
But isn't it coming from a negative direction?
But what would the sign of pi halves be? Positive or negative?
Oh, it would be positive.
That's all we're looking at is what is the sign of pi
So
halves?
you're not looking at like the direction it's going?
No, not the slope at all. You are literally, if I asked you to plug in, so pi halves, it would be like pi halves minus 0.01. So pi halves is like 1.57. You'd be plugging in like 1.4. So what makes it tricky is we can't analytically plug in 1.4. Our calculator could plug in 1.4, but we can't. So then we have to take into account that all students take calc, and you have to, it's like coming in from the opposite direction of what you think because we do it counterclockwise. That's, I think, what's tripping you, is that the unit circle is drawn counterclockwise. So that's why I tried to draw the real ones, but then I think you're stuck on slope now. So all I want you to do is tell me, is the sign next to this point positive or negative? Positive. Is the sign close to that point above it positive or negative? Positive. Positive divided by positive is a positive. If you come from this direction going to both of those same points, the sign coming from here is positive. However, the sign coming from down here, this point right here, infinitely close, is negative. So now you have a positive divided by a negative. So that's why you get a negative infinity coming from this direction. You could put it in your table. So let's do that. Go to your second window and hit table set. So we want our table to be near pi halves, right? So what I want you to do is make your table start pi halves. Because what we're going to do is we're going to look at it from the left and from the right. I want you to make your change in the tables 0.1. And then change the independent back to auto just for this purpose. So go to your second table now. Obviously the starting point is going to say error. And then just look at the signs near the error. So to the left, they're all positive, right? So if you scroll up, you can see the left of the word error. And if you scroll to the right, they're all negative. So when you're talking about an infinite discontinuity, all you care about is the sign to the left and to the right.
Okay.
Does that help?
Yeah, I think so.
I know it's a little tricky at first. And we're gonna look at another trig function. Because trig discontinuities, like we're not as comfortable graphing trig functions yet. So we're still kind of learning how to graph trig too. Like I said, if you look at the graph from 0 to 2 pi, I think that helps also. Because you can follow what you're tracing. Okay. So you guys did yesterday. So, all right, let's pick up with 2.2, day 2 finally. We're a little behind today. So yesterday we talked about slant asymptotes, and we talked about how do you find them, when do you find them, how do you see them. Well, a slant asymptote occurs when the numerator is one more than the denominator. And you've actually done slant asymptotes before, you just never realized that you were doing a slant asymptote when in Algebra 2 and trig, you did polynomial long division. Technically, when you were doing that, you were finding the slant asymptotes. We just didn't call them slant asymptotes. What we were doing was trying to factor and find the roots. So in order to find a slant asymptote, you literally set it up like you set up long division. Top divided by the bottom. So top goes in, bottom out, and then you set it up. What do you have to multiply x squared to get 3x cubed? Well, I need a 3x. Then you multiply back to each of the parts. So you get 3x cubed minus 3x minus 21x. And then when you do long division, you're subtracting that whole line. So 3 minus 3 is 0. 0 minus a minus is a positive. Minus a minus is a positive. And you bring down the 2.
That, like, second, should it be negative? Okay.
Thank you.
Just now.
There should be a square root, sorry. So again, then the question becomes, okay, what do I have to multiply x squared by to get 3x squared? So it becomes minus plus plus because you change the signs when you subtract the second. So they zero out. And then you get 24 over x plus 23. Now, here's the thing. A slant asymptote is linear. All of this is a remainder. We're actually done. This right here, that 3x plus 3, represents the slant asymptote. Once you have a line, you're done. A slant asymptote is an equation of a line. Think about when we write asymptotes in general for vertical and horizontal. Verticals are x equals because they're up and down. Horizontals are y equals because they're left to right. So this is a y equals, and it is an equation of a line. So today we're still just looking at limits involving infinity. Yesterday we were looking at answers going to infinity. Today we're going to look more at, okay, what if the limit is going to infinity. If the limit is going to infinity, we're really talking about horizontal asymptotes. So these are what we call end behavior models. So the limit as x goes to infinity of f of x over g of x will equal 1 if two functions f and g behave the same. We refer to this as end behavior models. Okay. So the next little activity we're going to do it on our graphing calculators. So what you're going to do is plug in two functions to f of x. We're going to plug in 3x to the fourth minus 2x squared, or 2x cubed rather, and then you're going to plug in 3x to the fourth. So we're plugging in two functions that are similar but different. So they have the exact same beginning. They're both 3x to the fourth. However, one function has other parts occurring. So you're plugging in f and g. What's really nice now is the graphing calculators are in like reds and blues, so you can see exactly which function is which. So put your standard window up. I know our window's been changed, so make sure you just hit like zoom 6 the first time you do this. That way it's a standard normal window. So when you do it the first time, do you see both the red and the blue function? Do they appear to be the same function? No. They both kind of look like a quadratic or a parabola, right? But like, don't really share points in common. The blue's a little bit higher. The red's a little bit stretched out. It's a little bit more wider, so it's compressed. So we look at them and we're like, these do not look the same. What I want you to do now is adjust your window. So we're going to go to the x's, and I want you to make them negative 20 to positive 20. And then change your x scale to be by 2s, so it doesn't. And then I want you to change your y values. Here's the killer, right? I want you to make it negative 10,000, positive 500,000, and make your scale 10,000. Now hit graph. So it's putting out the blue one. And it puts out the red one. And now, what once was 2 becomes 1. So what happens is as you get large, and we really didn't get that big, right? Your x's are only negative 20 to 20. That's not that far off from the negative 10 to 10 scale you just looked at. So what changed from negative 10 to 10 to negative 20 to 20 went from two totally different looking functions to 1. So that's what they're talking about when they're talking about f divides g behaving the same. If you look at something on a larger scale and you zoom it out, what was once 2 becomes 1. So they behave the same. So as you look at really, really big numbers, aka infinities, they'll act the same. So instead of trying to plug an infinity into something really crazy like this, you plug it into that. So if we compare these two functions analytically, what we're doing is that long division setup. So we're going to set it up so that it is F divides G. So if you have a single denominator, rule of sum is to break it up so it's under each numerator. Same thing divided by the same thing becomes 1 minus So you get the idea that the ratios simplify out to this. So then it says, let's look at the limit of those two ratios. So I have the simplification. Now we want to look at the limit as x goes to negative infinity of all of that. So that's like 1 minus, what's a 2 divided by something really big? So 2 divided by 1,000,000 would be anything kind of normal divided by something big becomes what? Small. So that kind of becomes a 0. 1 over infinity squared, 0. 5 over infinity cubed, 0. 2 over infinity to the 4th, super 0. So the limit as x approaches negative infinity of these two functions being divided is 1. If the limit as it goes to infinity of the two functions being divided is 1, they behave the same. So again, we showed it graphically, they behave the same when you zoom out. Analytically, they behave the same when you zoom in. Now, that does not mean, this is the difference, this does not mean the limit as x goes to infinity of f of x equals 1. It means that the limit as x goes to negative infinity of f of x is the same as the limit as x goes to infinity of g of x. Does that make sense? So this tells me that the limit as x goes to negative infinity of f of x equals the limit as x goes to infinity, negative infinity of g of x. And that limit as x goes to negative infinity, you plug in a negative number to x to the 4th, are you going to positive or negative? Anything negative to the 4th is positive, so positive times a positive is positive. And infinity to the 4th is going to be really big. So therefore the limit as x goes to negative infinity of f of x or g of x is infinity. Think about what your graph looked like too, right? We looked at negative 20 and it was up at 500,000. Think about it as you get bigger and bigger and bigger and bigger. The answer is just getting bigger and bigger and bigger and bigger. So the rule tells me they behave the same, meaning their limit at infinities are the same. In this case, it's an infinity. There may be times where the answer is an infinity. It could be a number. What would the limit as positive infinity be in this case? This is even or odd. G of x, even or odd? Even or odd? Even, right? G of x is even. There's only an even exponent. So since g of x is even, and behavior is the same. So if the end behavior to the negative infinity is infinity, the end behavior to positive infinity is infinity. Don't be afraid. You guys are smart. You know this. You got this. That makes sense, right? So same idea here. We have f of x. We want to find an end behavior model for f of x. So if you think about f of x, you have 2x to the 5th over 3x squared. What is the highest power of this function? So you have 2x to the 5th and 3x squared. So it's not really acting like a quintic. It's kind of acting like a, if you divide x to the 5th by x squared, what does that simplify to? X to the 3rd. So this function, when I graph it, isn't going to look like a 5th root or a 2nd root. It's going to look like a cubic. So an end behavior model would keep the same coefficients and then divide the exponents. So when it asks you to find a comparable model, you keep the coefficients and subtract the exponents. So the end behavior of all polynomial functions will behave like the end behavior of their largest monomial. So, and if you need like a hint, end behavior of polynomials will behave like the end behavior of their largest monomial division. So in this case, I took the biggest from the top and divided it by the biggest of the bottom to get the behavior of the same. Okay? We have g of x. The end behavior of a polynomial acts like the biggest monomials. So what is the largest monomial from the numerator? It'll be 2x cubed. The largest from the denominator is 5x cubed. So cubic over cubic becomes gone. So then the end behavior model for this is 2/5. Huh, it's a number? It's a number. The end behavior model is a number. What relation can you put to g of x with end behavior we already know about? I told you, end behavior kind of gets to a similarity with something for graphing purposes. Yeah, what do you think?
There is no asymptote.
The opposite. It is the asymptote. So think about the horizontal asymptote. What's the rule for horizontal asymptotes? If the top and bottom are the same, it's what? The top and bottom highest powered exponents are the same. What is the horizontal asymptote? It's the coefficients. H of x is literally the coefficients, right? So the end behavior model, in this case, because the top and bottom are the same, is the horizontal asymptote. The end behavior model is the horizontal asymptote. So again, in terms of graphing this, that 2/5 is acting like a bound. As this graph gets big, it acts like the graph of 2/5. So if it acts like the graph of 2/5, what that means is the limit, as this graph goes to negative infinity, or the limit as this graph goes to positive infinity for g of x or h of x is going to act the same. So that means as g of x gets really, 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 really big, it's getting really, really, really close to what? As g of x gets really, 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 really big, it's getting really, really close to and it's either going to be, we don't know yet, it could be above or below, right? So as we're getting really, really big, it's getting really, really close, either above it or below. Okay? Think about what this is. This is a positive. Would it matter if it's above or below it? Can this be negative? Is 2 fifths ever negative? So more than likely they're both going to be coming in from the positive side because the sign of this is positive, no matter what you plug in. So they should both be coming in from above. Again, taking into account the sign of that and the fact that I can't plug anything. Could it be any more distracting? Just trying to learn AP Calc here, guys. All right, I feel like your brains are kaputted. I'm going to stop you.